So let's talk about how, so far all we talked about was how the concentration changes, but we've never really specified time yet, right? We have this change in time, but let's say I want to know, well, how much has the concentration changed after 10 minutes? The rate law itself doesn't give you that, right? It does not. There's no time in this thing. Again, we know this is the change in concentration with time, but explicitly, there's no way to determine how much of the reactants I have after a given amount of time. Okay? So, how does it change with time? Well, a more useful mathematical relationship would show how the concentrations and time correlate to one another. So, for example, let's say I have a reactant A and it's just decomposing. Right? So this happens to a lot of molecules. When you heat them up, they just decompose. All radioactive decay reactions are first order. It's just a single reactant falling apart into a product. Okay? So we're going to keep, whenever we talk about time, we're going to keep our reactions very simple. Okay? It's just going to be our single reactant going to products. And again, it gets really, really complicated, really, really fast when you have more than one reactant. And we're not going to deal with that in this class. Again, if you take higher level chemistry courses in kinetics, we'll get into that stuff. You have to get heavy into calculus once you do that. Okay, and this is a non-calculus based course. Okay, now we know that average change, right, is equal to the rate. And since we're talking about the reactant here, which is disappearing, we had to put the negative sign in here. So the rate of disappearance of A is equal to the change in A with respect to time. And again, negative because the rate has to be positive. Okay. But then let's say it's first order. Our rate law is going to look like this. Rate is equal to that proportionality constant, the rate constant, times the concentration of A. Well, guess what? That rate equals that rate. These are the same rates. So I could say this equals this. Now, we're going to have to use some calculus. I don't expect you to redo this. I'm going to show you the equations that you need to memorize in the end. But if you know basic calculus, you can actually derive these equations on your own. Okay? So let's say I want to change this now from this average to instantaneous. So in calculus, what that means is we're going to replace this delta with a d, right? It's going to become a derivative. So it's going to look like this. It's going to be d over d. Then I'm going to rearrange it, right? This is dt, so I'm going to take that to this side of the equation, and I'm going to leave the k there, right? I also took the negative from this side and put it on that side. And then that is our dt. On this side, I have the dA, which stayed there, but then I divided both sides by the change in concentration of A, or the concentration of A. And then my boundary conditions are just from time zero. So the initial concentration at time zero, that's what this means right here, right? This is the initial concentration. And then the concentration at any time t. So those are my boundary conditions. So when you have the, take the derivative of a constant, which is just k, it's just the x then, right? So this ends up being, if we're going to say, well, t in this case, right? So this would be t. And then to our boundaries, 0 and t. So it's going to be, since this is t, it's going to be negative k times t minus negative k times 0, which then would be 0. So that means this side just ends up being negative kt. Now again, I'm not expecting you to do this, but this is just basic calculus. Okay. Now 1 over A, well, that's the ln of the concentration of A. Okay. So it would be the ln of concentration of A at time t minus minus the ln of the concentration at time 0, okay? Now, property of logs, if I have one ln minus another, the minus one goes in the denominator, and we could write it like this. So this could also be written as the ln of the concentration at time t minus the ln at concentration of time 0. But again, that property of logs allows us to do that. So this is what we call the time concentration equation, because notice that it now relates time to concentration. So this would be the time concentration for a first order reaction. This is also called an integrated rate law. So you'll hear me most often refer to it as time concentration of equation, but sometimes I'll call it an integrated rate law, because that's all this is. We integrated the rate law, and it gave us our time concentration equation. So we can see for a first order equation, we do need to know the initial concentration and the rate constant. And from that, I can tell you what the concentration is going to be at any time t. Okay? So you're just going to need to memorize this equation. Now, this ratio of the concentration at time t divided by the initial concentration, that's just the fraction of A that remains after a given amount of time t. So if this ends up being 0.25, that means 25% of the reactant remains after a given time of t. Does everybody understand that? Because that might be what I say. I say, well, how long does it take until there's only 25% of the reactant left? Well, that means that this ratio is 0.25. How much is left after, how long does it take for 75% of the reactant to be left? So in other words, only 25 of it reacted, 25% reacted. So you got to listen to the wording too. This is the percent of the reaction that remains. This is the fraction of the reactant that remains. If I want to know how much after 25% has reacted, that means 75% remains. That means this fraction is 0.75. Okay, is everybody good with that? Okay, let's do an example. So the decomposition of dinitrogen pentoxide into nitrogen dioxide and oxygen gas at 45 degrees Celsius is first order with a rate constant of 4.8 times 10 to the negative 4 per second. So that's the K value. The initial concentration of N2O5 for this experiment was 0.0165 moles per liter. I want to know, what is the concentration of N2O5 after 825 seconds have passed? So first off, it told us that it is a first order reaction. That is important. You need to know the overall order. I might tell you the individual orders, and then you'll have to determine what the overall order is. Okay? So I'm telling you it's first order. So that we're looking for a time. So that means we're going to use the time concentration equation for a first order reaction. So that's going to be the concentration of the dinitrogen pentoxide at time 0. That's the initial concentration. And then we're looking for the concentration after the time is 825 seconds. So we're looking for this. This was given to us, the initial concentration was given to us as 0.0165 moles per liter. K was given to us as 4.8 times 10 to the negative 4 per second. And the time, well, we're looking for 825 seconds later. So we got to rearrange this equation then to solve for this. Okay, so plugging in the actual values, it looks like this. We'll do this side first real quick. So that's going to give us negative 0.396. Okay, now to get rid of this is a log base E, right? That's what the natural log represents. Log base E. So if I raise this to the E, and this, it becomes just this. So if I raise this entire thing to the E, it simply becomes this. And then this is going to be E to this. We say that's the anti-log. Okay. So that looks like this then. So this then goes to this. Okay. Okay, now take E to that value and you get 0.673. Notice it went positive. Now all we have to do is multiply both sides by 1.6 times 10 to the negative 2, and notice that's where our units came from. Notice coming back here too, by the way, that our units canceled, because you cannot raise a number that has units, right? So this can't have units, because when I raise it to the E raised to that, this number, the exponent can never have units. We're going to violate that later on, but you really aren't allowed to do it mathematically, okay? Okay, so again, that gave us this. Then we multiplied both sides by 1.65. There's our units of moles per liter. And so 825 seconds later, it went from 0.0165 moles per liter down to 0.011 moles per liter. Now, if you're interested in understanding how an exponent's sig figs change, I'm not going to stress on that, but it is in that paper posted on Canvas. Okay. Again, I probably will mention it here and there, but it's not something I'm really holding you to. Okay. Okay. Any questions about any of that? So it's just knowing how to rearrange that equation and understanding properties of logs. Okay, let's talk about half-life. So half-life simply is the amount of time in which half of the initial concentration is gone. So in other words, that the reaction goes halfway through, right? So the half-life is when you have half the initial concentration. It's that time, it's how much time it takes for the reaction to go that you only have half the initial reaction concentration left. So if we have a first order reaction, right, if we have this initial concentration, then T, the half-life, is going to be when we have 1/2 of this. So we'd replace this with 1/2 the initial concentration. Okay. Well, now you can see that the A naughts cancel, and we have the ln of 1/2. Well, the ln of 1/2 is negative 0.693. And that's now going to equal negative K. And now we're going to replace T with the variable T1/2. Because this is specifically when we have 1/2 the initial concentration left. So this now becomes T1/2. And like I said, the ln of 1/2 is negative 0.693. So the negatives cancel, rearrange the equation for T1/2, and you have the half-life for a first order reaction of being 0.693 divided by its rate constant K. Now there's something unique about this and important about this equation. Notice that the half-life of a first order reaction, I don't need to know what the initial concentration was. It doesn't even appear there. Now that's really important for radioactive decay. Let's say I come upon some dump site where somebody dumped a whole bunch of radioactive material. Believe it or not, that's more common than you think. All I need is a Geiger counter to determine the rate of decay of that pile. And I could get from that how much material is actually there. So that's the importance of this. And I'll do some problems later on showing you exactly how you would do that out in the field. Okay. Okay, so for first order reaction, again, the half-life is independent of the initial concentration. It cancels out. This isn't going to be true for any other order reaction. You'll always need to know what the initial concentration was. Okay, so let's take an example. Let's say we have sulfuric chloride, and it decomposes into sulfur dioxide and molecular chlorine. So at 320 degrees Celsius, the rate constant is 2.2 times 10 to the negative fifth seconds. And I want to know what is the half-life of sulfuric chloride vapor at this temperature. Well, it tells us it's first order. So that means we know that the equation for the half-life of a first order reaction is this. So all we need is K. K was given to us. So I'm just going to plug in for K that 2.2 times 10 to the negative fifth per second. So our units now, we have 1 over a second, so our units are going to be seconds. Then just plug this into your calculator. Be careful. Make sure you're practicing. You can't type in 0.693 divided by 2.2 times 10 to the negative fifth. You will get the wrong answer. Okay? You either got to put this in parentheses or take 0.693 divided by 2.2 divided by 10 to the negative 5. Or 0.693 divided by 2.2 times 10 to the fifth. They'll all give you the same thing.
What about the E? You know what I mean?
There is no E. Where do you see E?
No, on a calculator, like 2.2, capital E.
Don't use
negative.
E. Don't use E. Use the E in your calculator. Don't ever.
E in the calculator.
Use your E on your calculator.
Yeah. Okay.
I'll do a problem and I'll show you. I'll physically show you my calculator. Don't type in the value of E. Use the E button on your calculator because it goes to something like at least 10 sig figs is where if you use it, you're probably only going to use it to 3 or 4 sig figs, 2.78, blah, blah, blah. Okay. So don't use the E button on your calculator, but there is no E here. So I'm not sure what you're talking about. Okay. Okay. So that gives me 3.5 times 10 to the 4 seconds. So in other words, it takes 8.75 hours for half of this sulfuric chloride to dissociate, to decompose at 320 degrees Celsius. Well, I could look at that graphically, right? So here was my sulfuric chloride. I had what, like 2, 4, 6, 8, 10, 12, 14, 16, 18. I had 24 sulfuric chloride molecules or moles, right? So 24. Then 8.75 hours later, I had half of that. I had 12. Now for a first order equation, that just keeps going that way. 8.75 hours later, for a total of 17.5 hours, I'm going to have half of this. So now I'm going to be down to 6. Then 8.75 hours after 17.5 or 26.25 hours, I'm going to have half again. So on and so forth. So again, this only applies to first order reactions because it didn't depend on the initial concentration. So that is half-life. Does everybody understand how half-life works? It's just the amount of time to go from the initial concentration to half. That all nuclear decay types of reactions, all nuclear decay types of reactions are first order kinetics. Okay, we've already seen that the half-life is simply the time required for half of the initial concentration to disappear, to be reacted. Well, a half-life then, when we're talking about radioactive material, simply means that half of the radioactive material has reacted and is no longer radioactive, or at least it's no longer the original radioactive material that it was. Okay. So, and like I said, all radioactive decay processes are first order. So that means that the half-life is independent of whatever the initial concentration was. We're going to do some homework problems and we'll see why that is actually really important in real life. Okay. So we're going to change the first order time concentration a little bit. Now remember, it used to be the initial, the concentration at time t over the initial concentration. Well, when we're talking about radioactive decay, we're usually talking about nuclei because we want to know how many nuclei disintegrate per second. So that's going to be our rate. Instead of having moles per liter per second as our rate, the rate of radioactive decay is going to be nuclei per second, where N represents the number of radioactive nuclei. So it's just going to be the radioactive nuclei at some time t divided by the initial number of radioactive nuclei. That ratio, we're going to take the ln of it, and that's simply equal to negative kT. So again, it's just a first order time concentration equation. That's why I didn't give you this as an equation of the equations to know, because you really already know it. You just need to understand for nuclear decay, you're replacing the concentrations with the actual number of nuclei, okay? Okay, so let's determine what is the half-life in years of technetium-99. So technetium-99 is actually a man-made element. It does not exist naturally on the Earth. We produce it in most nuclear reactors and for the purpose of usually medical research. So technetium-99 is what we would call a radioactive tracer. So given the decay constant for the beta decay, we're not going to get into radioactive decay, but so beta decay is one type of radioactive decay. There's alpha particles, there's beta decay, there's positron, there's all kinds of different types of radioactive decay. We talked about alpha particles. Those are just basically helium atoms without any electrons. The beta decay is just it's a type of an electron, very high energy electron. So given that the decay constant, now that's K, right? That's the rate constant. So the decay constant in nuclear decay is just the rate constant. So the decay constant or rate constant is 1.0 times 10 to the negative 13 per second. So we already know what the half-life for a first order reaction looks like, right? So I'm just going to take, there's our T1 half is equal to 0.693 over K. So we were already given K, so plug that into your calculator. That ends up being 6.9 times 10 to the 2 second. Now, most radioactive decay takes a considerable amount of time. Some doesn't, as we'll see, but most of it does take a long time. So that's why we want the half-life in years instead of having to use, we're still probably going to have to use scientific notation, but it's kind of hard to comprehend, 10 to the 12 seconds. So we're going to convert that to years. So of course, there's 60 seconds in a minute, so the seconds will cancel. There's 60 minutes in an hour, so the minutes will cancel. There's 24 hours in a day, so the hours cancel. And we're simply going to say there's 365 days in a year, even though it's more like 365.25. We're just going to use 365 days in a year. So the days cancel, and that gives us our years. So the half-life of technetium-99 then is 2.2 times 10 to the 5th years. Okay, so that again is, so let's say 1, 2. So that's 220,000 years. So it sticks around for a while, okay? So 220,000 years. So that's the half-life. Now remember, after 220,000 years, only half of the technetium-99 is decomposed. Then in another 220,000 years, another half of that will also decompose. So that means now 75% decomposed after 2 years, or 25% remained, and so on and so forth. So for first order reactions, you can use the half-life in that way. Any questions about any of that good stuff? Okay. Now, once we know the decay constant, we can calculate the fraction of radioactive nuclei remaining after any given period of time, right? Again, remember, this represents the fraction of nuclei that remain at any given time. Now, K, normally you don't find a decay constant for radioactive decay. What you find is a half-life, right? So when you look up for radioactive decay, what you're going to look up is the half-life, not the K value. But we know that the half-life is related to K is 0.693 divided by the half-life. So that's why we're replacing K in this equation with 0.693 over the half-life. Because again, when you look it up, you're not going to find K, you're only going to find the half-life for radioactive decay. Okay, so that's all I did is I substituted that in for the T. And now we could easily find the ratio that's left after a given amount of time, if we know the half-life. So phosphorus 32 has a half-life of 14.3 days. What fraction of a sample of phosphorus 32 would remain after 5.5 days? Well, since it's radioactive decay, we know that it's going to be the time concentration equation for radioactive decay. We know we're going to replace again, right? We know it's the ln of NT over NO is equal to negative KT. We're going to replace the K with 0.63 over T1 half. We now know that T1 half is 14.3 days. T is going to be the 5.5 days. Okay. So there it is. The days cancel. So this gives us negative 0.267. But I just want this fraction, so I got to get rid of the natural log. Again, we're simply going to raise both sides to the E. E to the natural log of N over T is just NT over NO. And then we got E to the negative 2.67. Plug that into your calculator, you get 0.77. That is the fraction remaining, or in other words, after 5.5 days, 77% of the phosphorus 32 still remains as radioactive phosphorus 32. Any questions with that? Okay. Next, let's switch to second order equation. So again, we're still looking at this very simple situation where we have a single reactant going to products. And if it's going to be second order with only a single reaction, that means the rate law is going to be rate is equal to K times the concentration of our reactant raised to the second, again, since it's second order. Again, that would be the rate of disappearance. So this would be the individual disappearance of A. And going through and doing the whole calculus that we did for the first order equation. And again, I won't go through that derivation here, but if you do the calculus, you end up with this equation here. So the time concentration order for equation for a second order reaction, 1 over the concentration at time T is equal to KT plus 1 over the initial concentration. Okay. Half-life, all we're going to do is replace again A of T by 1/2 A naught, and then solve for T, which then becomes T1 half. And once you do that, rearrange it, you get that the half-life is equal to 1 over the rate constant divided by the initial concentration. So the half-life for a second order equation, you must know the initial concentration, unlike that of a first order reaction. Okay. So again, each succeeding half-life this time is twice the length of its predecessor. Unlike the first order where it was just the same, every given amount of time you lost half. In this case, after a given amount of time you lose half, then you have to double that time to lose the next half, then double that time to lose the next half, and so on and so forth. Okay. But I'll show you again, it's easier just to use the equations to do that than try to figure out how many half-lives. But we'll do problems like that tomorrow, okay? And then if we have 0th order, well, of course, if we only have a single reactant, it's going to be rate is equal to K times the concentration of the reactant raised to the 0, since it's 0th order. But of course, any number raised to 0 is just 1. So that basically means that the rate law is just rate is equal to K, okay? So that's why this just disappears. And again, you go through and do the same calculus, right? Would bring this side over and then take the integral from time 0 to time T, and over here, the integral of A, or del A, from A naught to A of T. And when you do that, you get the time concentration equation that the concentration of your reactant at some time T is equal to negative KT plus the initial concentration. Okay. Okay. An example of zeroth order, a lot of catalysts are zeroth order. Okay, a lot of catalysts. As soon as you have increased the surface area to the point where you can't really get any more surface, then it's zeroth order. Doesn't matter how much more platinum you add, it just needed to be present for the reaction to occur. Okay. Okay, let's talk about graphing these things. Okay, so this is going to be real important for those of you doing the lab, because you're going to use graphical methods. You're going to use graphical methods to determine your rate laws. So if we have a first order equation, when we do graphs, we always want things to be linear, to be a line, right? A line is y equals mx plus b, where m is the slope and b is the y-intercept. So we need to somehow change this equation into a linear relationship. Well, property of logs, right, basically says this is the log of the concentration at time t minus the log, the natural log at the initial concentration, right? So we could rewrite it like that. And then I rearranged it. I just added the log of the initial concentration, which canceled it on this side, and put it on that side. So there it is. By just using the property of logs, I now have a straight line where this is y, this is m, this is x, and this is b. Here's our y. The m is negative k. The x is just our time. And b is positive, the ln of the initial concentration. Now we can plot then y versus time. So the ln of the concentration at a given time versus time. And we can figure out what k is that way graphically. Okay. So here's an example. This is just a decomposition of the N2O5 to nitrogen dioxide and oxygen. And so we just ran the experiment at the same temperature and just kept measuring the change in concentration over a bunch of times. And then we're going to plot then, again, the ln of the concentration at some time t, that's what this is, and then versus t, so that's just our time. So I took the ln of each one of those values, so now we're just going to plot this as the y and this on the x-axis, and that's going to look like this. Okay. Now it's negative because we've got negative t here, right? So I could fit that to it and I get a straight line. And so in Excel, for example, they call this linear regression a trend line. And from that equation then, you know the slope, and the slope's negative since it's going this way. So kt, negative k, is equal to some negative value. So whatever the positive value is just k. So you can find the rate constant graphically like this. Okay. So again, k is just the negative slope. For a second order equation, the time concentration equation is already given as a straight line. Again, this is y. M is just k this time, not negative k, but just k. X would be your t, and your b would be this positive 1 over the initial concentration term. Okay, so that's already a straight line. Okay, so we're just going to plot then 1 over the concentration at time t versus time itself. And again, if we did that for this reaction, so here we have the reaction of nitrogen dioxide forming nitric oxide and oxygen. So plotting that data, now notice this time I plotted it as the ln, as if this were a first order reaction, right? So here I plotted this as a first order reaction. But when I do that, I see that a straight line does not fit the data, it's curved. So that tells me that this reaction is not first order. So I'm going to do it again, but this time I'm going to plot it as a second order reaction. I'm just going to plot 1 over that concentration at time t versus time. That's going to look like this, right? So now I'm just plotting it 1 over versus time. And now I get a straight line. So in this case, the K is just equal to the slope. So since it's a straight line, I know it's second order. Okay. Okay, any questions about that? Okay, this is just a summary of everything that I just said. Okay, so there's nothing new to say here, but it's just easier for you to study from because you need all of these equations. Number 21 out of chapter 14. It says sulfuryl chloride decomposes into sulfur dioxide and chlorine gas. The decomposition of the reaction is first order, right? So that already tells us that the rate law is what? What is the rate law? If I tell you that it's first order, what's the rate law? Anybody tell me what it's going to be?
Rate equals the rate constant times the concentration.
Of?
Sulfuryl chloride.
And raised to what power?
Raised to the first power.
Yeah, it's first order. There's your rate law. So if I tell you what the order is, you can always tell me what the rate law is. Okay. Now, I don't think it asked for that, but it says the decomposition reaction is first order if the concentration of sulfuric chloride is 0.5 after 1 hour. So basically, it's telling us that the sulfuryl chloride concentration after 1 hour is equal to 0.0583 molar at 32 degrees Celsius when the initial concentration, and it's telling us then the initial concentration, which again is basically times 0, right, is 0.0631 molar. What is the concentration after 2 hours? So it's basically asking us what is the concentration of sulfuryl chloride after 2 hours. How do you think we're going to solve this? What method, concept, equation, what am I going to need? Look at what variables you have.
You'd use the first order integrated rate law, and then
Yeah, we're going to use the first order integrated rate law or the first order time concentration equation, right? We have concentrations and times. So for first order, that's the ln. And we're going to say it's A of t. Well, A of t is equal to this, right? This is A of t. So if I ask you to be specific and use the chemicals, you're going to replace A with SO2, CO2, because I want to make sure that you understand what these equations mean. Over A naught, which this then would be the A naught, and that's equal to negative the rate constant times time. Okay, so I want the concentration though after 2 hours, right? So that'll be this after 2 hours. I already got the initial concentration. I know the time's going to be 2 hours. But where's K?
you need to use the given information to solve the equation for K before plugging in 2 hours.
Exactly, right? I'm going to have to solve this equation twice. Once to find K, then I can plug it in again to find my concentration after 2 hours. So I'll just rearrange this real quick. So we're looking for K. So K is equal to this, which is the ln of AT over A naught divided by T, and we'll bring the negative over. You could solve it however you want. Okay, I just like to solve the equation for the variable. I personally think it's easier that way, because now I can plug this whole thing into my calculator as one calculation, okay, and not be making any mistakes by transcribing numbers or not using enough sig figs and have rounding errors because I'm rounding my intermediate values, okay? So then this is going to be negative, the ln. So the time at t, and we're talking about the 1 hour now, is 0.0583 molar. The initial concentration was 0.0631 molar. The time is 1 hour. And so now I'm not going to go through the sig figs on this, but we lose a sig fig, okay? And it has to do with the properties of logs and how to carry sig figs through logs. But we're going to end up with 0.9833. No, we're not. That was the last problem. We are going to end up with 0.07911 per hour. And again, it ends up being 2 sig figs, and that's because of property of logs. So basically, you have some intermediate calculations here. And basically, this intermediate here gives us 0.92393. Now, that's 3 sig figs. But when you take this whole thing, that actually equals negative 0.0791186. But when you're following sig figs through a log, the number of significant digits of the number that you're taking the log of is equal to the number of significant decimal places. So if this is 3 sig figs, we're going to go 1, 2, 3 decimal places. And this is why we end up with only 2 sig figs. Okay. Okay, so there's our K value. Now, we're going to use this equation again, except this time we're solving for A of t. Now, A of t is, we got to get rid of this natural log part. So we're going to take the anti-log, which means it's going to be e raised to it. So it's going to be e, which will give us this, and then this will be equal to e to the negative kt. That leaves us with this ratio on the other side. So now all we have is this ratio is equal to e to the negative kt. Now I'm going to multiply A naught. So just rearranging this equation gives us this. Again, if you're going to have to learn how to do this, right? Get rid of the natural log or log. And again, if you're uncomfortable with actually rearranging the equation, do it however you're comfortable with. Just make sure you're doing your homework and you're getting the correct answer, okay? Okay, so A naught was our 0.0631 molar, right? That was given to us. Then we have E, and that's going to be raised to the negative. Our K we just determined was 0.07911 per hour. And the T that we're interested in, right, is for 2 hours, right? So here T is equal to 2 hours. So that's the T we're interested in. So that's 2 hours. So we have let's leave that as an H, okay? So we have the H and the per H, they cancel. And so then we have, basically we have 0.0631 molar, E to the negative 0.15823. this number here is equal to 0.8536. Now, in this case, the number of decimal places equal the number of sig figs, right? Just opposite of what we just did up here. So the number of decimal places is the number of sig figs, so that's 2 sig figs. And then plug that into your calculator and you're gonna get 0.053865 molar. 2 sig figs, 3 sig figs, so this will only be 2. And so your final answer then is 0.054 molar. Number 23 from chapter 14 says the dimerization of a chemical process is a chemical process in which molecules react with itself to form new molecules called a dimer. So for example, butadiene, C4H6, reacts with itself to form a dimer with the formula C8H12. Okay, so basically what that means is we have two butadiene molecules reacting with each other to form just a single new molecule, H12. And so that is called dimerization. The order is second order with respect to C4H6. So if it's second order, that means the rate law is rate is equal to that rate constant times the concentration of our reactant. There is only one, and it is, so therefore it is second order. So the rate law would look like that. It says the rate constant, so that's K, right? So now we know that K is 6.4 times 10 to the negative 2 liters per mole per second at a given temperature. And the initial concentration, so that is the initial concentration, which we would write like this, is 0.0350 molar. Okay. So again, I encourage you to write, you know, the unit, I'm sorry, the variable with the value in units. Again, this is going to help you to solve these problems. It's going to help you to choose what problems you need. So it says, what is the molarity of C4H4 after the reaction proceeded for 1 hour, right? So we have a time of 1 hour. And so basically, what equation are we going to have to use here? So what equation am I going to need to use? Taylor, what do you think? What equation am I going to have to use to solve this?
You would have to use one of the integrated rate laws.
And specifically, which one? There's 3 of them.
The second order one.
Okay.
It would be 1 over the concentration of A times T equals KT plus 1 over the initial concentration of A.
And no negative in front of the second order. There is a negative in front of the first and the 0, but not the second. Right, so instead of writing A's, we could actually write the actual chemical formula into it. Okay, and so what are we solving for here?
You would be solving for the concentration on the left side. Right?
Yeah, right, the concentration at some time T. T, of course, being the 1 hour. Okay, so let's just leave it the way it is. So we'll just solve it like this. Let's see. So K was given to us as 6.4 times 10 to the negative 2 liters per mole per second And then the time was given to us as 1 hour. And we can see that the seconds and the hours aren't canceling, so we need to convert one or the other. So we know in 1 hour there is 60 seconds. Now the hours cancel and the seconds cancel, and we are going to get liters over mole. Now that's the inverse of molarity, but that makes sense because this is the inverse over here. Okay, so that's good. We got the right units. So that's going to give me then, oops, I forgot a part, didn't I? So plus 1 over our initial concentration, which is going to be 0.0350 molar. Okay.
Through the equation, it's 1 hour equals 3,600 seconds. Just 60, right?
Yes. Yeah, I should have. I was going from minutes to hours, and then yeah, you're right though. So yeah, you could either do that, right? We could say it's 3,600 seconds, or you can go from, you know, there's in 1 hour there would be 60 minutes, and then in 1 minute there would be 60 seconds. And that's why 60 times 60 is 3,600. So it'd be 3,600 seconds. Okay. Okay, so we have, so we'll plug this into our calculator then, and that's going to give me 230.4. Now remember, this is liters per mole. Well, that's just the inverse of molarity, right? And we could say plus, and then 1 over the 3, well, this is what, 2 sig figs, so we're right here. And then 1 over this value here is going to give me 28.571. And again, this is per molar, so it is per molar. This is 3 sig figs, so that'll go to there. Then plug that into your calculator, and you're going to get 258.97 per molar. We're adding now, so we're looking for the fewest number of significant decimal places. Well, the least precise is actually 2 in front of the decimal place. This is 1 past, that's a lot more precise. So we're going to have to go 2 in front of the decimal place. So that's 258.97 per molar. But we want the molar concentration, so we got to take the inverse of that, right? Because right now we had the inverse, so we're going to take 1 over that number. Plug that into the calculator, and that's going to give you a value of 0.003861. Now it's molar, right? We had 1 over molar, so it's molar. And it's 2 sig figs. So we could write that then in easiest to just write it in scientific notation so we don't have all of these zeros. So we're going to go 1, 2, 3, and when we're going to the right, we're subtracting. So it's going to be 10 to the minus 3. So it's going to be 3.9. Again, 1 past the last sig fig is 5 or greater, so we're going to round that last sig fig up. And then times 10 to the negative 3 molar. Okay. Any questions on that part of it? Okay, so the second part then says, how long will it take in hours for the concentration of C4H6 to drop to 0.005 molar? Well, it's just basically the same equation, right? Because it's a second order reaction, except this time we're asking how long. So that means we're going to be solving for T. So I'm going to say what KT is going to be equal to this. So 1 over the concentration of C4H6 at some time T. And then I'm going to subtract this from both sides. So that's going to be minus 1 over C4H6, the initial concentration. Okay. So just doing this part of it, then we have 1 over. So it wants to take how long in hours for the concentration to drop to? okay? And this is going to be from the original concentration. So this will be 0.050 molar. And then we're going to subtract the initial, which again was given to us as 0.035 molar. So 1 over 0.035 molar. That's going to give us 200 per molar minus 28.57 per molar. This is 2 sig figs. This is 3 sig figs. So when you plug that into your calculator, then you're going to get a value of 172.42 per molar. Again, this is the least precise. It's 2 in front of the decimal place. This is 1 behind, so we got to go 2 in front again. Now remember, that equals KT. So to get T, we're going to have to divide that 171.42 per molar by our K value. Now remember what our per molar is, right? Our per molar is normally molar is moles per liter. So this is going to be liters per mole. The only reason I'm doing that is because the units of K were given that way. Okay, so now we can see that our per moles cancel, our liters cancel. I now have 1 over a second. So these units are seconds. And it wants it in hours. So again, you could have used the 3,600 seconds in an hour, or if you're uncomfortable with that. Now remember, I'm going to move this, right? So that the per second is actually seconds up here, okay? So that's actually the seconds up here. So say 60 seconds in 1 minute, and then 60 minutes in 1 hour. So we see our seconds cancel, our minutes cancel, and we're going to get the units that we want, which are hours. So plug that into your calculator, and you're going to get 0.7440 hours. And what do we have? We have 2 sig figs, 2 sig figs. These are exact. So this will be 2 sig figs. And so your final answer then is going to be 0.74 hours. So it'll take approximately 45 minutes for it to drop to 0.005 from that initial concentration of 0.035. Okay, any questions about any of that? Then you could always ask yourself, does it make sense, right? So this is actually 5 times, right? This number here is 5 times 10 to the -3. And it took an hour to get to to 3.9 times 10 to the -3. So if this is less than an hour, then yeah, that makes sense, right? So you could always do these self-checks. Okay, any questions about that good stuff? Okay. Okay. Let's try another. This is number 28. It says dinitrogen pentoxide decomposes when heated, right? So we could have actually put this here, right? We could have said it's heated, to nitrogen dioxide and oxygen gas, according to this following equation. Okay, so if the rate constant for the decomposition of N2O5 is 6.4, so it's telling us that the rate constant is 6.2 times 10 to the -4 per minute. What is the half-life? So we are looking for the half-life. It says the rate law is first order in N2O5. So if the rate law is first order in N2O5, what's the order of the overall rate law? This is kind of a trick question, but it's simple. I'm not trying to trick you. I want you to be able to immediately realize what the wording means. So it's saying that it's first order in N2O5. Therefore, what's the overall rate law? Hannah, what do you think?
It's first order. There's only one.
It's first order, right? So how would I write the rate law then? Exactly what would I write? What would you write?
Rate equals rate constant times the concentration of N2O5.
Yeah, right to the first. So, and because it's only one reactant, and that reactant is first order, and it doesn't mention a catalyst, well, then the rate law has to be first order. So now we know that the half-life equation for a first order reaction is just 0.693 over the rate constant K. Again, that's why we need to know what the order is so that we could choose the correct time concentration or integrated rate laws. Okay, so it says how long, so wait, first, if the rate constant is this, what is the half-life? Okay, well, that's easy enough, right? We're just gonna plug into our equation. We just need the value of K per minute. It doesn't tell us what units it wants, so we'll just leave it in minutes. Okay, so remember we have 1 over a minute, right? Again, we have 1 over a minute. That's what that means, right? And then if we multiplied it by this, right? And remember, a minute over a minute, that's just 1, right? Because both the minutes cancel. So we're not changing anything. But I can see in the denominator, the minutes cancel, and we just end up with minutes. So you recognize this because you're going to see this all the time. If you have a per unit in the denominator, it just moves to the numerator. Okay, so plug that into your calculator then, and you're going to get 1.117 times 10 to the 3 minutes. This is 2 sig figs, so that would be equal to 1.1 times 10 to the 3rd minutes. So that would be the half-life. It wants to know how long will it take for the concentration of N2O5 to decrease to 25% of its initial value. How could we go about solving that? Caitlin, what do you think? How are we going to go about determining how much, how long it would take to drop to 25% of its initial value?
But we just take the half-life of the value we just got?
Well, okay, what does that mean? What happened after 1.1 times 10 to the 3 minutes? How much do I have left after that?
Oh, you only have half of its initial value.
What percentage is that?
50%.
So if I want to get 25%, then what?
You would need half of the 50%.
Right, or 2 half-lives, right?
Yep.
So I would just need 2 half-lives. So I'd have to say, okay, to get the 50%, right? So this was this was our 50%. So to get to our 25%, I just need 2 of my half-lives, right? 2 of my half-lives. So that's simply going to be 2 times this. Or again, you wouldn't have to rewrite all of this out. Just multiply that number by 2, right? So then that's just going to equal 2.235 times 10 to the 3 per minutes. Again, we have 2 sig figs. So that would be equal to 2.2 times 10 to the 3 minutes. So Kayla, what would I do if I want to go to 12.5% of the initial value?
wouldn't you just take the half-life of the 2.2 times 10 to the third?
Yeah, right. I mean, that's just, so half of that is 12.5. So yeah, it's just, you could take, it's basically 3 half-lives, right? So it's just 3 times the half-life. So now we determined the half-life was the 1.117, whoops, the 2 sig figs, get rid of that, times 10 to the third, okay? And so that's just going to equal 3.353 times 10 to the third minutes. Again, just 2 sig figs, so that would be equal to 3.4 times 10 to the 3 minutes, right? We had to round up because 1 past that last sig fig is now 5 or greater, so we rounded up.
Wait, for that one, do you still divide by the 6.2 times 10 to the negative 4?
I just took this number here.
Oh, okay.
I'm sorry, I didn't mean to confuse. I just took this. This is the half-life, right?
Mm.
So this is just that half-life. So that's why I just did that.
Oh,
We
okay.
could have done the same thing for this one too, right? I could have just taken 2 times that value because that's all this is. Okay. Now, let's say it isn't a nice one like this, right? What, or you just blanked out during the exam because for no reason at all you panicked yourself, which you should never do. Okay, so there's actually an easier way of doing this. So this is first law or first order, and by the way, the only reason this works is because it's first order, right? If it was second order, remember it takes 1.5 times each time for it to go down, right? So it's different. You couldn't use this, you couldn't do this for anything but a first order. But we know that the first order rate law, time concentration equation, I should say, is the ln of the concentration at some time t over the initial concentration, which is equal to negative kT. Remember, this represents what? This ratio represents what? How much has reacted, or is how much is left? What is this ratio?
What fraction of the sample is left?
Right, so this is the fraction that's left, right? So fraction that's left. So if I want to know how long it takes until 12.5% has reacted, or I should say it's left, I'm sorry, right? So this is when 12.5% is left. How could I use this equation to do it? They didn't give me the initial concentration or even what the concentration was going to be at the end. So instead of doing this, how could I solve it using this?
In the percentage.
Not the percentage. What do I need? Your right idea, but not the percentage. I can't put 12.5 here. What would I put there, Michael?
You scroll the paper then.
Oh, I'm sorry. What?
Not like the other way.
Which? Oh, this way? So
Yeah,
what?
I don't know.
So he's on the right track, but what does he need to do? This is a fraction. This is a percentage. How do I convert that to a fraction, the 12.5?
You could divide it by 100%.
Yeah, right. If I just take the 12.5%, divide it by 100%, the percents cancel, and we're going to get 0.125. So if I want to know when there's only 12.5% left, I just take the ln 0.125 equals negative KT. Now K we know, right? So K is the 6.2 times 10 to the negative 4 per minute. And that gives us our T. So T then is simply going to equal the ln of 0.125 over negative 6.2 times 10 to the negative 4 per minute. Now this number here is negative. When it's less than 1, it's going to be negative. When it's greater than 1, it'll be a positive number. So the ln then, so the natural log of 0.125, you can see it's negative 2.079. So that's going to cancel out this negative. And then you'd simply divide it by the 6.2 times 10 to the negative 4. And you get, whoops, times negative 1, okay? And you get 3.353. So that's 1, 2, 3. So that is going to end up being 3.4 times 10 to the 3 minutes. Exactly what you got by doing it that way. In my opinion, this is the easier way to do it than using half-lives. This question was just kind of showing you what happens for the half-life of a first-order equation. Okay? Okay, any questions about any of that? Okay, let's try another. So this is radioactive iodine 131. Radioactive iodine 131 is commonly used as radiation therapy to help treat some types of thyroid cancer, since thyroid cells naturally take up radioactive iodine. An average dose taken in pill form contains 95 milligrams. So we have 95 milligrams of this radioactive isotope iodine 131, which has a half-life. So it has a half-life of 8.05 days. Assuming that all the radioactive iodine remains in your body, how much in milligrams iodine 131 remains after 31 days? Right, so we're looking for the mass of iodine 131 after 31 days. Okay, so how am I going to go about solving this problem?
Solve for the variable in the log function.
Well, okay, what function? What equation?
The one we used in the last problem.
Yeah, right. Again, remember, radioactive decay is always first order. So, you know, normally though, it's going to be the concentration at time t over the concentration, the initial concentration. But one thing that is different when we're talking about radioactive decay, we're not talking about concentration, we're actually talking about the number of radioactive nuclei. So instead of the concentration at time t, we're going to say the number of radioactive nuclei at time t, and instead of the initial concentration, we're going to say the initial number of radioactive particles, okay? And then that's just equal to negative KT. Now, again, for radioactive processes, they don't give us K, so how can we get K?
You can derive it from the half-life formula.
Yeah, right. We know that the half-life for a first order equation is just equal to 0.693 over K. So therefore, K is going to be equal to 0.693 divided by the half-life. So I could rewrite this and say that, okay, this is negative 0.693 T over our half-life. Okay, everybody see that? Okay, now what are we solving for then again? I'm sorry, what were we solving for here? We want the mass of iodine 131. So what are we solving for in this equation? Kaylee, what do you think?
N naught.
N naught,
Wait, NT, my bad.
NT, right? Because that's actually the final after 31 days. Okay. Well, okay, that's another question. And where are we getting N naught from? How are we going to get N naught?
You to get it from the initial weight of.
Okay, so this mass, right? So you're saying I want to get N naught. I'm going to write that way down here, though. Okay, so N naught. You're saying I'm going to get that from this guy here. Okay, so how am I going to get the number of radioactive nuclei from this mass? Do numbers, actual numbers, ever have units? Is 24 a number? Is 24 a number? Eugenie, is 24 a number? If I tell you you have 24 eggs, do you know how many eggs you have?
24.
So 24 is a number, right? What are numbers in chemistry?
They're numbers when they have million.
I didn't hear you.
Like,
So a baker uses dozens to talk about numbers. What does a chemist use to talk about numbers? Anybody, what does a chemist use to talk about numbers? If a baker uses dozen to talk about numbers, what about chemists?
Units?
Pardon me?
Units?
Well, a dozen is a unit.
Yeah.
is it moles?
It's moles, right? When chemists talk about numbers, they talk about them in terms of moles. So how do I get to moles?
You convert the milligrams to grams and then grams to moles.
Okay, how do I convert the milligrams? Okay, so we'll do that then, right? So there's 1,000 milligrams in 1 gram. So now we have grams. Now how to get the moles?
You divide by the molar mass.
The molar mass. Now I will tell you this, the molar mass of an isotope, right there it is. Now that's only accurate to 3 sig figs, but that is the molar mass of an isotope. Okay, that's so, and that only works for isotopes. It doesn't work for just regular iodine because that's a mix of isotopes, right? In this case, we're talking about a single isotope. So in this case, there's 131 grams of the iodine 131 in 1 mole of iodine 131. Now the grams cancel, and I have moles. But we need the absolute number. How do I get the absolute number? So in other words, if I have 24, well, I got to get rid of the dozen part. I need it to be a unitless number. Right now we have moles, but I need a unitless number.
Multiply by Avogadro's number.
Yeah, right. So Avogadro's number says there's 6.022 times 10 to the 23rd iodine 131 nuclei per mole of iodine 131. So now the moles cancel, and I actually have the individual number of nuclei. So you'd plug that into your calculator, and you'd get 4.367 times 10 to the 20 iodine 131 nuclei. So there's now the individual nuclei. Okay, so we can plug that into the equation. I'm going to rearrange this equation real quick. So we're just going to rearrange it. We're solving for n of t. So first thing I'm going to do is I'm going to take e, or I'm going to raise both sides to the e power. That means this side is going to become n over t over n naught, and this side will become e raised to the negative kt. Then I'm simply going to multiply both sides. So that's going to be n of t is equal to n naught e to the negative kt. And again, if you aren't comfortable with doing that, you can just fill in the blanks and then solve it however you want. But again, I like doing this because I can plug it one thing into my calculator. Okay. Okay, so now we know that this, whoops, and how many sig figs? 2 sig figs. So this is going to be 4.367 times 10 to the 20 nuclei. That's the iodine 131 nuclei. Then it's going to be e to the negative, and then this whole quantity, okay? So K, again, was given to us as a half-life, so we're going to have to write that as 0.693 divided by 8.05. And now T1 half is already in days, right? Because this is days now to the days. So T then is in 31 days, so I don't need to convert that to seconds or anything else. So I'm just going to put 31 days because they're just going to cancel and we're good. And then we're going to get the actual number of nuclei. Okay, so plug that into your calculator then. And you are going to get 3.028 times 10 to the 19 nuclei. So you still have a whole lot left. And it's only going to be the 2 sig figs. And then to get back to the mass, right, because it wanted this in terms of milligrams, the mass, not the number of nuclei. So now to get the mass of the iodine 131 left after 31 days, we'll start with the number of nuclei. So 3.028 times 10 to the 19 nuclei. We'll convert that to moles. So we're going to say 1 mole of the nuclei is 6.022 times 10 to the 23rd nuclei. Nuclei cancel, and now we have moles of nuclei. Now we need the molar mass of the iodine 131, except we're going to multiply it by, so there's 131 grams of the nuclei in 1 mole of the nuclei. And again, this is all for iodine 131. The moles of nuclei cancel. Now I have grams, but it wanted it in milligrams, and we know in 1 gram there is 1,000 milligrams. So the grams now cancel. I have milligrams, and that's going to give you 6.587 milligrams to 2 sig figs. So that's going to be 6.6 milligrams of the iodine 131 remain after 30 days. So it dropped from 95 milligrams to 6.6 milligrams in just 8 days. Okay, is there any questions about that? Now, there would have been I wanted to show you this because depending on what the question asks, you might need to go through this step. But in this particular case, if I'm just going from milligrams to milligrams, look at each one of these steps. They are opposite one another. So really, I could have just made this real simple and just plugged in for time, the initial concentration, just the 95 milligrams, and we would have came up with the same answer. I'd have had to still do this, but I could have eliminated this entire step. But you need to recognize that. You need to do the homework, okay? You need to do the homework. Okay, is there any questions about that? Okay, now, there's other ways to solve this. We could have asked, you know, I might have said that, hey, look, you have, you found this pile of nuclear waste, and you know that the nuclear waste is iodine-131. And you took a Geiger counter, and you measured the radiation with a Geiger counter. And it gave you some amount, right? I'm just making up a number here, but let's say it's 6.6 times 10 to the negative 4, and the units would simply be per second. What would this represent? What variable would this represent? Again, this is why it's so important to look at the numbers. You got to know what variable you're talking about. So this is actually, which we don't usually put, but we could say this is nuclei per second. What variables have these kind of units? Rate constants do. But is this the rate constant? No, the Geiger counter measures the rate of disintegration or radioactive decay of the particles. So what is the variable for this? Let me say it again. A Geiger counter measures the rate of radioactive decay. What variable is this? The rate. This is the rate. So if you're given that, you're going to have to use the rate law. Rate is equal to K. Now, again, remember, it is the concentration, but in nuclear terms, we just say N raised to the first. So now if you know the half-life, right, we would actually replace this. We would say this is 0.693 over T1/2 times the number. Now you could tell me the number of nuclei, but I might want to know what mass. So now you're going to have to use this type of equation to get the mass. So you still need to know how to do this. Even if we didn't need it for this problem, you still would have needed it for this problem. Do your homework. There's going to be problems like both of these types that I just talked about will be on the quizzes. The quizzes pretty much give you every possibility you can have.